Hi everyone, welcome back to week 13 of MEM 23006A Apply Fluid and Thermodynamics Principle in Engineering. Before we start, disclaimer, this online recording is intended for internal teaching only within South Metropolitan TAFE Carlisle WA campus only. You may not either directly or through the use of any device or other means copy, download, upload, publish the content unless expressly permitted by South Metropolitan TAFE in writing. Alright, let's have a look at our DAP here. We are sitting in week 13 and your exam in week 17. So as per now, we haven't had any further instruction about how we're going to conduct the exam. My understanding at this point, you may need to come to campus during daytime to do the exam, but let's discuss that a bit later. As we know from the news, the WA government is planning to lift up the restriction. We might be able to come back to class for the exam. Now, as usual, we are on week 13 today. I'm just gonna discuss fluid and hopefully buoyancy. If not, in week 14 we'll discuss a little bit of buoyancy, and then we'll talk a little bit of our project here. And in week 15 I'll just going to give you a review on the theoretical question that we're going to ask you or expect you to answer during the exam. And week 16 we're going to do the revision of all the calculation. It's similar like the first term. Then on week 17 exam, and hopefully you finish both assignment 1 and 2 in week 19. As usual, your formula sheet is here. Keep it handy. Make sure you are familiar with it. Now, in week 13, we actually going to discuss fluid. So we move away from the gas from week um, 11 and 12. We discuss multiple gas processes, which is kind of fluid anyway, but the one that we going to discuss today is more like the fluid as as a liquid that and a little bit of gas that we going to review. Now a little bit of summary here. I'm not going to go this on details. Fluid in thermodynamic, it can be liquid, it can be gas. Sometimes it mix of solid particles as well. But a liquid with solid particle is known as slurry. Okay, so we're not going to do slurry in this course. When I was at Curtin University, slurry is the subject of itself in year 4, I believe, is on thermal, no, it's on the fluid mechanic. Year 4 is advanced fluid mechanic where we discuss slurry. The other name of slurry is what we call non-Newtonian fluid, or the fluid that doesn't follow the Newton law. Well, what we're going to discuss here is just a Newtonian fluid. Now I'm going to jump from chapter 8. We're going to come back to chapter 8 work example in a minute, but I'm just going to jump quickly to chapter 10 here. So what we are interested here to discuss is fluid statics. So we're not talking on the fluid dynamic. I leave it to you when you're going to uni later on, when you pursue your academic career. But we want to do simple analysis using fluid static. Now there are 3 important basic principles that I would like you to know and remember before we attempt the work example. Principle number 1, if the fluid is static, then the pressure at any point in a static fluid is the same in all directions. Principle number 2, the pressure as well as the force at any point on the wall of a vessel containing static fluid is perpendicular to the wall. Remember, we're talking of static fluid. If the fluid is dynamic, then this principle do not apply. The third one, which is important, and then we use this principle quite a lot, is a pressure applied to an enclosed fluid or system of enclosed fluid at rest is transmitted without loss in all direction throughout the system. So this principle 3 or Pascal principle is widely used in hydraulic system. You know, when you see a bin truck come in the morning with the fork coming out from the side, picking up your beans, which is 100 kilos, they use a little tiny hose containing an oil at a pressure. So you have a pressure pump, you got oil, and then the pump pressurize the oil, and the oil is moving the fork. So what we can see here, if you have a piston or a pump exerting a pressure in the closed system, then the same pressure will be transmitted without loss in all direction throughout the system. Remember, we're talking of pressure. Now, pressure is different than force. So pressure equal to force divided by area, if you remember that from term 1. The pressure is the same, the force is different because the pump here might be smaller than the ram. If you look this diagram here, maybe you remember there's a hydraulic lift. Maybe if you put your car into service, the mechanic press the button, and then this hydraulic lift will go lift your car, which is at least 1 tons. But I don't know if you had the chance to see the little piston or little pump is very tiny compared to how much the weight it need to be lifted. It's same in the mining as well. You have a big machinery lifting up tons of load is using the same principle. So the principle 3 is quite handy. Right, let's jump back to question 815. I'll leave the other question to you because it's kind of similar with what we discussed in term 1. Remember when we discussed the basic principle of mass, pressure, force, and things like that. Relative density, you are the expert of it. So I'll leave that to you for practice. What I'm going to do, going to have a look this question 8.15. So remember principle 3, this is a hydraulic jack, so we have 200 Newton coming in here, or a piston at 20 mil cylinder. Remember the pressure is the same. The pressure here will be the same at, in here at all direction. And this is a force, or there is a weight on it that we need to lift up. And the cylinder is bigger, is 100 mil instead of 20 mil. So let's have a look. Let's have a look the question. The question is, what is the fluid pressure? And question B, what is the ram force here? Okay. Now I've transferred that diagram into this, so I don't have to draw it. Now question A, if you remember, what is the fluid pressure? So we do not want this force, this is a force. We want what is the pressure here? What is the pressure that being exerted by this little pump. So question A, do you remember? Pressure, in this case, is the fluid, equal to force divided by area. What is the force in here? So the fluid here, so this is a fluid there. So the fluid being forced by 200 Newton. And the area is the surface area of this piston. So we have a 20 mil there. Remember, the surface area of the circle is not given on your formula sheet. So it's quarter pi d square. Remember, this is millimeter. So we have to convert that to meter times -3. So that will make this from millimeter to meter. And don't forget to square it, because quarter d square is the surface area of the circle. Okay, so that make it meter square. So Newton per meter square is the unit for pressure, or another word, Newton per meter square is actually Pascal. That's why it's called Pascal principle. So we put our number here is 636942667 Pascal. If we take 6 of it, so 1, 2, 3, 4, 5, 6 out, so it becomes 0.64 megapascal. And this is a gauge pressure. Remember last week when we discussed the gas process, everything are on absolute. Now on the fluid we use just a gauge pressure. So that's question A. So this is the fluid pressure. So this pressure, 0.64 megapascal, will be transferred in all direction by the fluid without loss through here. So the fluid is pushing it by 0.64 megapascal there. The question B was asking what is the force of the ram, which is there. Now we can see here the surface area of this piston and this piston is different. This one is bigger. So using the same formula again, pressure equal to force divided by area. Now for question B, the pressure here will be the fluid pressure. Remember, the fluid pressure is the same everywhere. So we put that back in. We put 636. For this one, I'll make it in kPa. 942 kPa. So remember, this is Pascal. So 636,942.67 Pascal. So in here 636.942. So kPa equal to force of the ram divided by not the surface area of the cylinder, but with 100 mil. Again, quarter d square. Have to convert the 100 mil into cubic meter. Don't forget to square it. That's the meter square. So force of the ram is 5. Now what's the unit? Kilo Newton. Why is kilo Newton? Because we use kPa. If you're not using kPa, if you're using PA, then will be 5,000 something Newton. Okay, you just need to be consistent with the unit. Alright, let's clean the board. Okay, let's have a look another example here. We have example 10.2. So we have a tank filled with oil about 2.5 meter high, and there is the gas here as well. So we have a pressure on top there, pressure gauge at the bottom, and we are given the relative density of oil is 0.9. The question is, what is the gauge pressure 2 or P2 when the pressure at P1 or the gas pressure is 0? Question B, when the gas pressure at positive 25 kPa. And question C, what's the P2 when this gas pressure is negative 10 kPa on, or in other words, is on vacuum. So let's have a look this quickly. When the, the pressure at 1 is 0, I'll just do this, so P1 equal to 0. Do you remember what's the formula to calculate the pressure of the fluid from the Bernoullis? If there is a static pressure like this, so P equal to rho, which is density, multiplied by gravity, multiplied by h, or the height of the fluid. So when P1 is 0, then we're just going to neglect the top here. So the pressure at 2, in this case, is P2. Density of the fluid is relative density 0.9. So the remember the formula, relative density equal to density of the fluid divided by the density of water. So if we have 0.9 relative density, density of fluid divided by density of water is always 1000. So the density of the fluid is 0.9 multiplied by 1000 is 900. So this case, the density of the oil is 900. Multiplied by constant gravity is 9.81 meter per second square, multiplied by the height. So the height here is 2.5 meter. So P2 is 22.1 kPa. Now I jump to kPa here, but this equation, what's the unit? The unit is actually PA, Pascal. Okay, just on the final answer, I just make it short to kPa. When you do it in your calculator, you have to divide it by 1000 to get into kPa. Now question B, what if P1 is actually 25 kPa? So now if the gas on top of the oil is 25 kPa, then P2 here is the pressure of the fluid here at 2.5 meter plus 25 kPa of the gas. So in this case, we know will be 25 kPa, so that will be the gas, plus the pressure exerted by the oil was 22.1 kPa. So total P2 now is 47.1 kPa. Okay, so there's a 25 kilopascal extra because the gas is under pressure. Question C, what happens if P1 is actually negative 10 kVA? So what's the P2 here? Well, so P2 is negative 10 kPa plus 22.1 kPa, which is the fluid. So P2 will be 12.1 kPa. It's not that difficult, isn't it? So let's have a look. Another example is quite similar. Now we have a closed tank fitted with piezometer like this. So what's the pressure at piezometer entry? So at this point, this is the entry at 100 mil above the bottom of the tank. B, what is the base of the tank? And C, what's the pressure of the vapor space? The liquid here is kerosene, and the relative density is 0.78. So this is quite similar to what we just discussed before. Now question A, at the piezometer entry, so at this point. So that is the question A. A, pressure at piezometer entry. Same formula, P equal to rho times G times H. Now at the piezometer entry, the H is actually from here to here. So what's that? 200 plus 600. So at the entry is 600 high. Sorry, 800 high. Again, density, the density of kerosene. So if the RT is 0.78, you just need to multiply it by 1000. Density of kerosene is 780 kilogram per cubic meter multiplied by acceleration of gravity multiplied by the H is 800 mil or 0.8 meter. So the pressure is 6.12 kPa. Question B. What about the pressure at the bottom of the tank here? So that's the bottom of the tank. Well, the bottom of the tank is 800 plus 100. So the bottom of the tank, the H will be from here to here, which is 900. So do the same thing again. 780 multiplied by, instead of 800, now it's 900. But don't forget to convert it to meter. So it's 0.9, 6.89 Pascal. Now question C. Well, what about the vapor space there? Well, the vapor space here is 200. Do the same thing again. So 780 kilogram per cubic meter times gravity times zero point 0.2 meter. So P is 1.53 kPa. Just a note, the vapor space pressure causes a rise on the piezometer by 200 mil. Okay, so if there is no vapor space here, the water there will be equal with the water level here, like that. But because of this vapor space is pushing the fluid down, then there is a fluid coming out or up in the piezometer, and the fluid is coming up from this surface of the water by 200 mil. So that is our vapor space. Okay, so our vapor is actually 1.53 kPa, exerting a pressure down to the fluid, which cause the fluid in piezometer to rise. Hope that makes sense. Okay, let's consider another similar example here. So we have a tank, and the tank has an air at about 200 mil. After that, we have an oil 300 mil deep. Then we have water 1300 deep to the bottom of the tank. Now the tank is connected to manometer like that, and the manometer is containing mercury, which has the relative density of 13.6. Now the blue solid color here is for mercury. Okay. So the water coming from the tank is the clear bit here up to there is pushing the mercury down and subsequently pushing it up by 80 mil. So 50 here is at the center point of the X entry of the manometer is 50. 150 here is the distance from this mercury line to the bottom of the tank. So the total mercury being raised is 50 plus 80, so 130. Now the question is asking what is the pressure here and what is the pressure at the bottom of the tank. If you have a look this system, you can actually calculate the pressure quickly at by using the manometer. So what I'll do, I'll just gonna draw a line here at the entry of the mercury there. I'm just going to call it X. So the pressure at XX, it's simply pressure equal to rho times G times H, so nothing changed. But we can calculate this very quickly because we have the mercury manometer here. So the density here now, we're going to calculate the density of mercury, which is 13 0.6 multiplied by 1000. Remember, this is relative density. You just multiply by 1000 to get the density of mercury, multiply by gravity, multiply by h. Now, which height that we're going to use? We're going to use the height from the tip when the mercury meet the water on this side here to the top of the mercury surface. So between the tip when the water meet the mercury to the mercury surface is 50 plus 80, okay, which is 130 mil. So we're going to convert it to meter. So the pressure at XX is 17,344.08 Pascal, which means the pressure that being exerted by the combination of the fluid here, so air, oil, a little bit part of the H2O at this point is 17,344 Pascal. Now, how that's gonna help us to find the pressure at the bottom? Well, the pressure at the bottom is an additional height of the water, which is 150, right? Because 150 is from here to here. So that's the remaining item that we need to calculate for that bottom. Okay, from the entry of that to the bottom. Pardon me, not from the entry, from this point here is 150. Because when this is how much water has been managed to push the mercury down. So from this point to the bottom of the tank is 150. So pressure at the bottom of the tank will be the pressure at point XX, what we already calculated before, plus the pressure exerted by the water with a height of 0.5 meter or 150 millimeter. So pressure at point XX is 17,344.08 plus rho times G times H. But now this one is the density belong to water, which is 10,000, gravity, and the height is 0.15. So if we calculate this, we got 1471.5 Pascal. So pressure at the bottom will be 17,344 plus 1,471. You got 18,815.58 Pascal or 18.8 kPa. Now, the next question is, what is the pressure of the air? Well, we're just gonna do reverse now. Let's come back to point XXX here. Remember, when we talking about point XXX, is the pressure, is the combination of the pressure of the air, the oil, and the H2O. But what you need to be aware is the height of the water up to XX point here is 1300, sorry, up to that point there, when the mercury meet the water, is 1300 minus 150, so 1150. Now we can write pressure of the air is actually pressure at x, x, x. I think I draw the x wrong. So x is from this point there. So not at the entry of the um, manometer. That's why I call confused. So point x is this point. So that x, x. Okay. So pressure of the air is xxx minus P H2O at 1.15 meter minus P oil at zero point 0.3. Does that make sense? So Pxxx we know, PH2O we don't know, we just need to calculate it. Density of H2O is 10,000 multiplied by G multiplied by 1.15. Oil, same formula, rho GH. So density of oil is 900 multiplied by gravity multiplied by zero point 0.3. So if we calculate that, water is 11,281.5 Pascal, oil is 2648.7 Pascal, and this is still the same, 17344.08. So that minus 17,000 minus 11,000 minus 2,600. So the pressure of the air, what you got is 3,413.88 Pascal. So that is the air pressure. So hope this makes sense. Bit apologize of the XX here. Again, XX is not at the entry of manometer. XX is the point where the water meet with the mercury. So come back here on work example. If you look example 10.2, so this is the last example we're going to discuss today. I'll just going to leave the buoyancy next week, and we hopefully talk a little bit of the assignment as well. So question 10.2 is similar to what we have before. What I'm going to do, just going to pinch this, but I'm going to change the number. So back to 10.2. We have a hydraulic system similar like what we have before, with the reciprocating piston pump. Now the diameter is 13 mils. The stroke is 20 mil, means the piston goes up and down by 20 mil. The piston force is 150 mil, and the pressurized oil is applied to ram, diameter 100 mil. Question A, what's the hydraulic pressure? Then question B, what the force of the rams? So question A and question B are similar to what we had calculated before in previous example. Now the only difference is question C. If the pump stroke is 20 mil, in other words, the pump moving up and down by 20 mil, what is the cycle of the piston if we want to move the ram by 500 mil? So that's question C. I just transferred the previous drawing. As you can see here is 150 newtons instead of 200 newtons. So this is a pump, 13 mil diameter. The stroke is 20 mil, and we have ram on another side. So we want to move the pump, sorry, the ram by 500 mil. So question C, how much this pump has to go up and down to move the ram by 500 mil. So that's question C. Let's have a look question A first. So question A is asking what is the hydraulic pressure or fluid pressure. So we have a pump. What's the fluid pressure? So pressure, force equal to area. We know the force is 150 Newton. The area is quarter pi times d square. So 13 mil, remember, multiply 10 to the power -3 to make it meter and square it. So the hydraulic pressure here, what we have is 113,066. No, sorry. 113,066.7.4 Pascal. So 1,130,667 or 1.13 megapascal. Okay. Question B, what is the force on the ram? So again, pressure, force ram divided by area of the ram. So the pressure here will be the fluid pressure. Remember, the fluid pressure will be the same everywhere. So we have 1,113, sorry, 1,130,667.4 Pascal force of the ram. Now the area of the ram is 100 mil of diameter. So quarter pi 0.1 meter square. Force of the ram is now 8875.73 Newton. So force, the unit is Newton. Pressure, the unit is Pascal or megapascal. Now question C, number of cycle for the pump to go up and down to move RAM by 500 mil. Now the best way to look into this to solve the equation is we look the volume. So when we have a stroke, remember this is a cylinder, you're looking at plan view or from side view or two-dimensional view, but actually this is a cylinder. So when you have a diameter of the pump, then you have a stroke, then you have a volume, the same with the RAM. So we can say volume of the pump multiplied by number of up and down will equal to volume of the RAM, given it's gonna move 500 mil, right? So if we find the volume of the pump at single stroke, sorry, at 20 mil stroke, but the single say going down, and we multiply by number of time to get the volume of the RAM at 500 mil. This is what we want. This is a number cycle of the pump. So we can calculate the volume of the pump, we can calculate the volume of the RAM. Then we can find the number of the cycle. So in this case, the volume of the pump would be quarter pi times 13 times 10 to the power negative 3 square. So that's the area. The stroke is 20 mil, so 20 mil. So that's the length multiplied by number of up and down equal to volume. The RAM is the same. So instead of 13 mil, you got 100 mil now. So 0.1 square. So that's area. And we want to move the RAM by 500 mil. So it's 0.5 meter. Now once you calculate this value and this value, you can solve number of up and down is 1479.2 times. Can you see what we're trying to do here? By calculating the volume of the RAM, we can match the number of the cycle required if the volume of the piston is only this much. Okay, so that's it for today. We will see you next week.